Now I would like to discuss the superposition of elementary flows that we have learned earlier. For example, uniform flow and doublet flow, or other type of flow. So in this special case, I will obtain flow around a stationary cylinder by adding a uniform flow with a doublet, and I will show you further details. Now consider the combination of a uniform flow and a doublet pointed to the left. The axis of the doublet is parallel to the uniform flow and in opposite direction of the flow field. Here I have provided you further details of the potential and stream functions for uniform flow and for doublet flow. Now if I go and add the potential function for both these flows, I will obtain the potential function for flow around a cylinder. Similarly, for a stream function, if I go and add the stream function for uniform flow and the stream function for doublet flow, I will obtain the stream function for flow around a cylinder. Once I obtain the stream function or potential function, I can easily determine the velocity distribution. Once I have the velocity distribution, I can easily determine the location of stagnation points, and also I can find the velocity at the surface of the cylinder. And finally, I can obtain the pressure distribution at the surface of the cylinder. Moreover, I can also determine the equation of a streamline, and this I will show you in the next. Now, as I mentioned, the potential function for flow around a stationary cylinder is obtained by adding potential function for uniform flow and doublet. And here you can see that the potential function for flow around a stationary cylinder. Subsequently, I will determine the velocity distribution, the UR and U theta, radial and tangential velocity components. Now here are the details of radial component. I have utilized this formula and performed the differentiation of the potential function. Similarly, for tangential component, I have used this formula and performed the differentiation of the potential function. Subsequently, I have written these two components here in this form, and you can see that UR and U theta are obtained for flow around a stationary cylinder. Next, I will introduce some simplifications. Now I would like to mention here an important boundary condition for an inviscid flow field. That is, the velocity is always tangent to a solid surface. So if I have my cylinder, at this cylinder at an arbitrary location, I have my tangential velocity, which is U theta. So my UR will be in my radial direction, and this UR will be 0 for the inviscid flow field. So by setting the UR radial component of the velocity for flow around a cylinder, I have obtained the value of the radius of the cylinder, and I will call this the radius of the cylinder capital R. I will indicate this. So this is my capital R, the radius of the solid cylinder. Subsequently, I have represented the radial and tangential velocity components in terms of capital R, the radius of the cylinder. And here are the equations of these two components, the radial component and the tangential component. Next, I will go and determine the location of stagnation points. Now, to find the location of stagnation points, I have set the total velocity at the stagnation point equal to 0, which has resulted in the radial and tangential component equal to 0. So once I have these equations for UR equal to 0, it has provided me the value of the radius, and u theta I have set equal to 0. In this factor cannot be 0, so I have to set sine theta equal to 0, and which has resulted in the value of theta, which is 0 and pi for my stagnation point. So I have two stagnation points, and the coordinates of stagnation points are r0 and r pi. So schematically I can show here that for flow over a cylinder, this is my location of my first stagnation point r and angle 0 theta, and this is the location of my other stagnation point. Make sure that angle is measuring from this axis. Next, I shall determine the tangential velocity at the surface of the cylinder. So here is the expression for my tangential velocity at the surface of the cylinder. By setting r equal to capital R, I have obtained this equation. Subsequently, I shall go and determine the pressure distribution at the surface of the cylinder utilizing the Bernoulli's equation. In order to determine the pressure distribution at any arbitrary point, let's call r theta, I will utilize the Bernoulli's equation. So I can write down the Bernoulli's equation for a point in the free stream region and any arbitrary point r theta. So make sure the subscript infinity indicates the free stream values. I can also write down the Bernoulli's equation in this form, and I am calling this equation star. Now the velocity here v square has two components, radial and tangential. And since I am looking for pressure distribution at the surface of the cylinder, so my radial component will be 0, only tangential component will exist. So it will be my v square ultimately. So I will go and put this value in equation star to further simplify the equation of pressure. After substituting the value of v square in equation star, I have obtained this equation, and I have further simplified this equation to obtain this form. On the left hand side, I have defined a dimensionless parameter known as coefficient of pressure or pressure coefficient, indicated by Cp. So the equation for dimensionless pressure distribution over a cylinder can be written in this form now. And next, I will go and plot this dimensionless pressure distribution over the surface of the cylinder, and I will show you in the next slide. This figure represents the distribution of Cp versus angle theta. So I have expanded the circular surface of the cylinder into a horizontal line on the x-axis. So angle is starting from 0 to 360 in degrees. So theta is in degrees. Now on y-axis I have Cp, and 0, above 0 the value of Cp is positive and below 0 is negative. Also note that at 0 on x-axis I have my rear stagnation point, and the coordinate of that is 0, r and 0. And 180 degree I have my second stagnation point, the coordinates are r pi. So Cp is positive starting from 0, having a maximum value of positive 1. Then it starts reducing towards the shoulder of the cylinder till it reaches a minimum value of -3 at 90 degree. Subsequently, it starts increasing again and reaches a positive value at the front stagnation region. This is front stagnation region of the cylinder. And after that, again it starts reducing to minus value and subsequently starts increasing towards the positive value. Now I would like you to plot this CP versus theta in the Excel file to check to see how your figure look like. It should come out the same. Furthermore, I have represented the pressure distribution onto a circular cylinder also, and you can see here the negative values are at the upper and lower, and positive pressure are at the front and the rear portion of the cylinder.